Hello everybody. First, I would like to thank the organizer for inviting me to contribute to this webinar. My name is Krisa Delva Sutanto. Today, I would like to talk to you about the roles of vitamin B in metabolisms. And hopefully, this will act as a springboard for discussion. First, I would like to explain about vitamin B1 or thiamine. In carbohydrate metabolisms, the process of glycolysis will cause pyruvate to be converted into acetyl-CoA by the pyruvate dehydrogenase. In the next process, in the citric acid cycle or Krebs cycles, alpha-ketoglutarate will be converted to succinyl-CoA by the alpha-ketoglutarate dehydrogenase. Both of these enzymes require thiamine. Thiamine is an enzyme cofactor that plays a role in oxidative and non-oxidative process of carbohydrate metabolism. In oxidative metabolisms, thiamine pyrophosphate or TPP is required in the pyruvate dehydrogenase complex process, which is responsible for the conversion of pyruvate to acetyl coenzyme A. Besides thiamine, pyruvate dehydrogenase itself requires other vitamins such as riboflavin, niacins, and pantothenic acids, so that in a deficiency state, the ability of pyruvate to enter the mitochondria through the pyruvate dehydrogenase complex decreases. Then, pyruvate will be converted to lactate through lactate dehydrogenase. Second, TPP as a cofactor of alpha-ketoglutarate dehydrogenase, which acts as a conversion of alpha-ketoglutarate to succinyl coenzyme A in the Krebs cycle. This process also requires the cofactor niacins and pantothenic acid as a coenzyme A. Accumulation of alpha-ketoglutarate can also indicate the occurrence of thiamine deficiency. However, the Krebs cycles will continue if there is interference with alpha-ketoglutarate dehydrogenase using the glutamate and GABA pathway. This process accounts for 10% of Krebs cycles activity. In the non-oxidative metabolic pathway, thiamine pyrophosphate as a coenzyme for the transcatalysis reactions, which is found in the pentose phosphate pathway. In this pathway, glucose in its 5-carbon form, called pentose, plays a role in the synthesis of nucleic acids and NADPH for the synthesis of fatty acids, maintain the myelin sheaths, and plays a role in the transmission and function of nerve membrane. Disruptions of alpha-ketoglutarate dehydrogenase causes an increase in alpha-ketoglutarate that crosses the blood-brain barrier. An increase in alpha-ketoglutarate causes it to be converted to glutamate. Furthermore, glutamate will be metabolized in GABA. As we know, GABA is an inhibitory neurotransmitter, so that decreased activity of alpha-ketoglutarate dehydrogenase causes inhibition of energy formation, which in turn will lead to accumulation of lactate in the brain. This causes irreversible damage to neurons. Thiamine deficiency also causes the increase of eNOS. Then eNOS synthesizes nitric oxide in neuron and respond to glutamate. Nitric oxides can react with superoxide radical to form peroxynitrate, which is toxic to neuron. The following are food sources of vitamin B1, among others obtained from brown rice, white rice, bread, potato, and also from animal food such as chicken, beef, and fresh milk. Now we continue to vitamin B2 and B3. The active forms are FAD and FMN for enzymatic reaction in the TCA cycle and fatty acid oxidation or beta oxidation. The macronutrients, carbohydrate, protein, and fat, after being pyruvate, will be converted to acetyl-CoA. This process involves 8 enzymatic reactions that produce an ADH and FADH2, which will transfer energy from the TCA cycle to electrons transfer. The formation of TCA cycle pathway, in this case succinyl-CoA, is also produced through the synthesis of analyprotics, namely alpha-ketobutyrate from the methionine cycle, and the synthesis of oxaloacetate from the pyruvate. Food sources of vitamin B2 can be obtained from rice, bread, potatoes, and mushroom, as well as from animal proteins such as chicken and beef. The daily requirement for vitamin B3 is 12 until 16 mg per day in men and 12 up to 14 mg per day in women. Food sources of vitamin B3 can be found in tuna, beef, chicken, and mushroom. Now we continue about vitamin B7 or biotin. Vitamin B7 is a coenzyme of pyruvate carboxylase, acetyl-CoA carboxylase, and propyl-CoA carboxylase. First, pyruvate carboxylase is a key enzyme of gluconeogenesis which converts pyruvic acid into oxaloacetate. This process requires vitamin B7. Second, acetyl-CoA is the starting material for the biosynthesis of fatty acid. Acetyl-CoA carboxylase will convert acetyl-CoA to malonyl-CoA, and the malonyl-CoA is used for fatty acid biosynthesis. And the last, valine and isoleucine that generate propyl-CoA, which is converted to succinyl-CoA by biotin and vitamin B12 requiring reaction. The following picture is that food sources of vitamin B7 or biotin with daily needs about 20 until 30 microgram per day. As we see, one egg has a vitamin B7 content of a third of the daily requirement. The other food sources of this vitamin are chicken, beef, mushroom, and cheese. And we come to the discussion of the last group of vitamin B, consisting of vitamin B6, B9 or folate, and B12. In figure A, dietary folate is converted to dihydrofolate, which is reduced to tetrahydrofolate by the enzyme dihydrofolate reductase. THF is converted to 5,6-methylene THF by the serine hydroxymethyltransferase, concurrently with the serine hydroxylation to glycine, which require vitamin B6. Thymidylate synthase use 5,10-methylene THF as a methyl donor for methylation of deoxyuridine monophosphate to produce deoxythymidine monophosphate. This process regenerates THF. 5,10-methylene THF can be reduced by methyl ethylene tetrahydrofolate reductase to 5-methyl tetrahydrofolate using B2 as a cofactor. As a part of methionine cycle, 5-MTHF donates a methyl group for the conversion of homocysteine to methionine catalyzed by methionine synthase, and in this case require B12 as a cofactor. S-adenosylmethionine is methylated during the methyltransferase reaction to form S-adenosyl homocysteine, and then hydrolyzed by S-adenosine homocysteine hydrolyzed to form homocysteine. Homocysteine also enters the transsulfuration pathway, catalyzed by cystathionine beta synthase and vitamin B6 to form cysteine. In the liver, betaine from the diet can act as a methyl donor for betaine homocysteine as methyltransferase, using vitamin B6 as a cofactor to make methionine and dimethylglycine as a byproduct. In figure B is about B12 and propionate metabolisms. The catabolic propionate pathway cleaves branched-chain amino acid, chain fatty acid, and cholesterol for using in the TCA cycle in mitochondria. Methylmalonyl-CoA mutase convert methylmalonyl-CoA to succinyl-CoA using B12 as a cofactor. Succinyl-CoA then enters the TCA cycle. The daily requirement for vitamin B6 is about 1.3 until 1.7 mg per day for men and 1.2 until 1.5 mg per day for women. Food sources of vitamin B6 can be found in banana, avocado, carrot, salmon, and fresh milk. The following are foods rich in folic acid, which are mainly obtained from vegetables and fruits such as avocado, orange, papaya, banana, Brussels, broccoli, asparagus. And the last is the food sources of vitamin B12. As seen in the following picture, the sources of vitamin B12 is from animal products such as salmon, tuna, beef, egg, and chicken. Thus, caution in vegetarian against the risk of vitamin B12 deficiency. I sincerely appreciate your attention today. I hope what I have shared will be beneficial for all of us.